chapter in the book. We're only going to do up through combined gas laws. The one section we're going to skip is Dalton's law of partial pressures. I really don't think we need to do that for one chapter. Okay? So, let's just review what we said a little bit last time. We're talking about the state of matter, the gaseous state. We saw little videos that showed gas particles bouncing around madly within a container. And I pointed out that there was lots and lots of space between them. Further, the particles traveled in a straight line until they hit either the walls of the container or each other. Because of that, they have an indefinite shape, and they take on the shape and volume of their container. That's simply because they just keep traveling until they hit it. There's so much space in between them. That means that you can squeeze them down, compress them, or you can make the container larger and they'll just travel further. So they can be compressed and they can expand. And finally, because they diffuse so rapidly, if you put a gas in one corner of a container with nothing else in it, it will distribute throughout the container very, very rapidly, so that any sample you take out is going to be uniform. Now we looked at Boyles Law. Boyles Law simply deals with the pressure-volume relationship. We said that Boyles Law simply said that the relationship between volume and pressure was inverse. And that simply means that the higher the pressure, the smaller the volume. Now we'll do a lab on that on Wednesday. A very, very simple lab. All you do is squeeze a syringe and take about 6 measurements. I will post some plotting software online, and as part of your report, what I'd like you to do is to simply do an analysis of volume versus 1 over P. Put those numbers in, plot them out, print the plot as a PDF file, print the PDF, and then attach that to your lab report. That's a nice thing to do, a nice way to submit written material to a lab or whatever. All right, well, we said that volume and 1 over pressure was proportional. The trick that we learned was that whenever we had the proportionality symbol, we could replace that with an equal sign and a constant. For any one gas system, this constant will be the same number. For different gas systems, it'll be different. All right, well, we could take this and we could solve it this way and say pressure multiplied by volume is going to be a constant for any one system. Now we looked at 2 systems, one where we had very little pressure on our piston and one where we had a lot. Now just qualitatively, when our pressure is small, 1 over P is a large number, therefore we have a big volume. When our pressure is large, over here, 1 over P is a larger number. That means that volume is smaller, and we have a little tiny volume here. Because this is the same gas system, we know that our initial conditions here, P1, V1, must equal our constant. Likewise, when we increase our pressure here, P2, V2 must also be the same constant. So if both of these are equal to the same number, the same constant, we can combine them and say that pressure volume for our initial state must equal pressure volume for our final state. This is the mathematical expression of Boyles Law. Any questions? All right, well, let's do a quick problem here. Hush, think about how you would set this up, and go ahead and work it out. What we basically have here is 12.5 liters of a gas at 1 atmosphere. The pressure is going to change to 800 millimeters of mercury, and we want to know our final volume. This is a classic Boyles Law problem, and we know that PV1 is going to equal PV2. All we have to do is take this equation, rearrange it so that we solve for V2. Now, as we look at our problem here, we should note that we have pressure given in 2 different units, atmospheres and milliliters. One requirement is that everything must be in the same units. So when we type in P1, V1 here over P2, we're going to have to make sure they're all either millimeters or atmospheres. 1 atmosphere, this is, by definition, atmospheric pressure at sea level, 25 degrees centigrade. That's called standard temperature and pressure, STP. We could take our 800 millimeters here. Remember that 1 atmosphere, that's a definition, is by definition 760 millimeters. So we could change our 800 millimeters into 1.053 atmospheres. Simply divide by 760. Remember, when we're talking about 1 atmosphere and 760 written just like this, those are considered definitions and exact numbers. All right, so plugging these things in. 1 atmosphere, 12.5 liters, that's V1, P1, and this is P2. Atmospheres will cancel, do our simple math, and this is 11.9 liters. Any questions? Yeah.
Where did you get the 760 from?
760, if you recall, maybe this to a second or third slide that we did last time. We defined, or we noted that on the mercury barometer, the height of the mercury column at 1 atmosphere was 760 millimeters. So that's where the link between 1 atmosphere and 760 comes from. Oops. This is the same as 1 atmosphere. We could have changed this to 760 and done it all in millimeters. It's up to you. Either way works. I put this little reminder in here. Once again, when we do 1 atmosphere or we do 760, those are exact numbers, and we don't include those when we do significant figures. If this had been 1.01 atmosphere, that would be 3 significant figures. But when it's written just as 1, that's exact. We also looked at Charles's law. Charles's law is the temperature-volume relationship. And we saw a cute little movie with a balloon and liquid nitrogen. Our conclusion was, or our observation was, when we cooled the balloon down, that it essentially deflated, it became small. When we warmed it back up, it became large again. That's a direct relationship. So we said mathematically that volume was going to be directly proportional to temperature. Higher the temperature, larger the volume. Now, like we did with Boyles Law, we're going to replace the proportionality symbol here with an equal sign and a constant. When we do that, what we're saying is that if we have the same system, the relationship between volume and temperature can be described simply as an equality if you include our constant here. We rearranged this to isolate our constant, and we said that volume over temperature for any system is going to be constant. All right, now if we have a two-state problem, where we're starting at one temperature or whatever and we're changing it, we can use this relationship in this form where we have initial and final temperatures and volumes. Remember, they're both equal to the same constant. That's why we can simply drop the constant out and say for the same system, V over T equals V over T. This is the expression for Charles's law. Here's a simple problem. We have 50 mils of gas. Our temperature is 26.4 degrees centigrade, and we're going to heat this up until our temperature is 374 Kelvin. We're looking for our final volume. All right, we are heating our sample up. So step one, the mental game you want to play here. You're heating it up, you expect your volume to get larger, don't you?
Yep.
So you want to set this up, or when you work your problem, just make sure that the final volume's a bigger number, so you haven't set it up wrong. We're going to do V1 over T1, V2 over T2. And we're going to solve this in terms of our final volume. The one thing we have to remember, whenever you do temperature and gas law problems, the temperature must be given in Kelvin. Okay, it must be Kelvin. Now, we did an experiment where we determined what absolute zero was, the extrapolation. It was minus 273 centigrade. So that means you can convert centigrade and Kelvin simply by taking centigrade and adding 273 to it. For this, we have 26.4. We're going to add 273 to it, and we're just about 300 Kelvin. Now, for most problems that will work in this course and on exams or whatever, you don't need to worry about 273.15. 273 is what you need. All right, we can now substitute in here, solve this for our final volume. It's going to be V1 T2 over T1. Simply cross multiply. Substitute in our numbers. We have 50 mils. We have our final temperature here at 374 and our initial temperature at just about 300 Kelvin. Yeah,
You can't cross multiply because they're not the same constant.
right. They are the same constant. So in order to solve here for V2, all we have to do is multiply both sides by T2. So we multiply, so T2 comes up top, and T1 stays in the denominator. So these two are together, and it disappears out of here. Simple basic. All right, substitute in. Our volume here is going to be in terms of milliliters, because that's what we were given. It can be anything. Our Kelvin is going to cancel. And this is 62.4 milliliters. Any questions? Now, we started to look very quickly at a tutorial for Charles' Law. We went through the one for Boyle. Let's go ahead and follow that up. Here we have a gas system, and we're given an initial volume in liters. When the volume changes to 0.197 liters, we have our temperature here at 209 Kelvin. What we're looking for here is our initial temperature. Now the problem, again randomly, this is done randomly in the computer, wants the final temperature in terms of centigrade. So we're going to get our answer in Kelvin, and then we're going to subtract 273 from it in order to make it centigrade. Because remember, centigrade plus 273 is Kelvin. I'd write that one on my card. All right, we want to identify our initial volume, our initial temperature, final volume, final temperature, and it looks something like this. We're looking for T1, we know T2. Again, we want to express this in centigrade when we're done. Both of our volumes are in terms of liters. That's good. They can be anything as long as they're the same. All right, we're going to rearrange Charles' Law again and solve it now for T1. T1 is equal to V1 T2 divided by V2. If you have trouble with the algebra here, just practice it a few times. It's just simply cross-multiplying, pick out the variable you want. When we substitute in, this is our initial volume. This is our final volume. This is our final temperature, 209. Do our math, and this comes up to be 461 Kelvin. Finally, in order to enter your answer, you need to convert Kelvin to centigrade. Remember, Kelvin minus 273 is centigrade. On the tutorial, just remember you don't put in units, as always. Same thing on Blackboard. On your last quiz, we will redo this material. Basically, it's going to deal with Chapter 9. Not going to put Chapter 12 on our quizzes. We're just going to look at that so that everyone understands Chapter 12. Not going to test on it. Okay? That's organic. All right, let's go ahead. I will hush for a moment, and you guys set up this one. Here, our initial temperature is 436 Kelvin. Our final temperature is going to be 164 Kelvin. So we're cooling it, aren't we? If we cool it, we expect our volume to decrease. Our final volume is 5,040 milliliters. We're looking for our initial volume. Problem says liters, so we're going to have to divide what we get by 1,000, or simply convert this to liters. Line up your knowns and unknowns. Our volume here was 5,040 milliliters. Remember, there are 1,000 milliliters in every liter. So this is the same as 5.04 liters. There's our initial temperature and our final. Take Charles's law, V1 over T1, V2 over T2, and solve it for V1. V1 should be V2 T1 divided by T2. So we take that, we substitute in our numbers, 5.04 liters. Here's our two temperatures. Our final temperature is, for initial temperature was 436, our final was 164. This is 13.4 liters. Any questions? All right, let's do our last ideal gas law here. And in order to do that, I'm going to go back to the experiment, board experiment that we did for Charles's law. Remember, we took different molar amounts of a gas. Could be any gas at all. And we changed its temperature. As we did, we measured the volume. Charles's law tells us as the temperature goes down, the volume goes down. Nice direct relationship. And that was good. But we can take these data and look at something else. Let's go out here to one temperature. Let's just pick a temperature. And let's just look at these volumes as a function of the numbers of moles. Now, as you look at this, as the number of moles increases, the volume increases. That's not too surprising, really. I mean, you'd expect that. As you put more gas in, as you blow into a balloon, it gets bigger. Putting more air in, it gets bigger. So, if we take these data and simply make a plot, we can call this Avogadro's relationship. And what we're going to do is the mole-volume relationship here. The plot that we get looks something like this. It's linear. The more gas you have, the larger the volume. Now again, that's not surprising. You probably could have predicted that. This is Avogadro's law. Remember, Avogadro has a number, 6.02 times 10 to the 23rd. But this is Avogadro's law. The number of moles and the volume is a direct relationship, just like temperature. All right. We have three things now. We did Boyle, where we said that volume was inversely proportional to pressure, right? We said we had Charles's, where the volume was directly proportional to temperature. Temperature goes up, volume goes up. And we just did Avogadro. Same sort of relationship. The number of moles goes up, the volume goes up. Those are our three basic gas laws. Let's just break here for a minute